About 4.6 billion years ago, a cloud of cosmic dust and gas drawn together by the force of gravity collapsed to form the Sun, laying the foundation of our solar system. From this cloud also emerged planets, which fall into two distinct categories based on their physical characteristics, the terrestrial and the Jovian planets. The terrestrial planets are the innermost members of our solar system and are characterized by their rocky surfaces, compact sizes, and metallic cores. These include Mercury, the closest to the Sun, full of craters from many impacts, Venus, which is covered in thick clouds of sulfuric acid, and its surface is so hot it could melt lead. Earth, with its metallic core, and Mars, with its big volcanoes and wide canyons. Past Mars, we encounter the Jovian planets, Jupiter, Saturn, Uranus, and Neptune. These giants have thick atmospheres of hydrogen and helium. But these planets, like everything else in our solar system, circle around the Sun. To understand why, we have to travel back to the time of Johannes Kepler, who established the fundamental principles of orbital dynamics, which were later refined by Isaac Newton. Kepler's laws of planetary motion describe how planets orbit the Sun in ellipses. In these elliptical paths, the Sun is positioned not at the center, but off to one side, at a specific point known as a focus. We measure these orbits with something called eccentricity, which is a measure of how much an orbit deviates from a perfect circle. Most planets have nearly circular orbits with eccentricities close to zero, meaning a relatively stable distance from the Sun throughout their journey. However, anomalies such as Pluto's orbit, with its higher eccentricity, lead to significant variations in distance from the Sun, influencing its icy surface conditions and atmospheric behavior. Pluto's path is noticeably tilted compared to the ecliptic plane and even crosses Neptune's orbit. Kepler's laws also tell us that planets sweep out equal areas in equal times, meaning they move faster when closer to the Sun and slower when farther away. This is because, according to Newton's law of universal gravitation, the gravitational pull between two objects depends on their masses and the distance between them. So as a planet gets closer to the Sun, the stronger gravitational pull accelerates the planet, causing it to move faster and vice versa. While each planet follows its unique path around the Sun, they simultaneously spin on their own axis. This spin, or rotation, has profound effects on a planet's shape and the way we perceive it. Typically, astronomers determine this rotation by measuring the planet's rotation compared to a fixed point in space, normally distant stars. This is called the sidereal rotation period. These are different from solar days, which is based on the Sun's position. For example, on Earth a solar day is 24 hours, while the sidereal day on Earth is slightly shorter, of about 23 hours and 56 minutes. This helps astronomers understand the true rotational speed of a planet without the complicating factor of the planet's orbit around the Sun. The sidereal rotation periods are determined using the Doppler effect, which is a phenomenon where the frequency of waves, including light, changes due to the motion of the source or observer. When a planet rotates, parts of its surface move towards us while others move away, causing slight shifts in the wavelengths of light we receive. By measuring these shifts, astronomers can determine how quickly a planet spins, revealing the length of its day. This rotation has a remarkable effect on the shapes of the larger gas and liquid-covered planets like Jupiter and Saturn, leading to a phenomenon known as oblateness, which is the flattening at the poles and bulging at the equator due to the centrifugal force generated by rapid rotation. These gas giants rotate at such speeds that their equatorial regions are significantly wider than their polar diameters, giving them a distinctly oblate appearance. We can also determine the mass of these planets through the orbital motion of its moons or the gravitational influence it exerts on nearby spacecraft or other planets. This is because Kepler's third law of planetary motion gives us a direct relationship between the orbital period of a moon and the mass of the planet around which it orbits. If we want to know the radius of a planet or its size as well, we can determine this through direct observation. Telescopes can measure the apparent size of a planet in the sky, and when combined with the distance to the planet, its physical size can be calculated. For planets without nearby spacecraft to take direct measurements, the timing of transits, or when a planet passes in front of its star from our viewpoint, can offer precise size estimates. Beneath their surfaces, planets reveal a diversity of internal structures, influenced by their chemical compositions, densities, temperatures, and pressures. Terrestrial planets, with their rocky exteriors, often have a layered structure, a dense metallic core, a silicate mantle, and a crust. In contrast, the gas giants lack solid surfaces, featuring instead dense cores surrounded by layers of metallic hydrogen, helium, and other gases. The ice giants, Uranus and Neptune, present a mix, with icy mantles enveloping their cores in gaseous atmospheres above. The surface and atmospheric composition of a planet plays a crucial role in determining its observable color and appearance. Mars, with its iron oxide-rich surface, appears red, earning it the nickname the Red Planet. Venus, covered in thick clouds of sulfuric acid and carbon dioxide, reflects a bright yellowish-white hue. But the gas giants show more variety. Jupiter's bands of ammonia crystals and sulfur compounds create a tapestry of browns, reds, and whites, while Uranus and Neptune's methane-rich atmospheres absorb red light and reflect a serene blue. The composition of a planetary atmosphere can also tell us about the planet's origins, geological activity, and potential for hosting life. For example, Earth's original atmosphere formed from the gaseous materials present during its accretion and was likely composed of hydrogen and helium. However, this primary atmosphere was stripped away by solar winds in the early stages of the solar system's formation. The secondary atmosphere emerged because of volcanoes, with gases released from Earth's interior, including water vapor, carbon dioxide, nitrogen, and others. This outgassing, coupled with the contributions from comet impacts, set the stage for Earth's atmospheric evolution. Over time, photosynthetic life forms began to convert carbon dioxide into oxygen, gradually transforming the atmosphere into the nitrogen-oxygen mix we breathe today. But Venus's dense, carbon dioxide-dominated atmosphere creates a runaway greenhouse effect, leading to surface temperatures hot enough to melt lead. The gas giants, such as Jupiter and Saturn, have atmospheres primarily composed of hydrogen and helium, with traces of methane, ammonia, and water vapor adding to their colorful appearances. Many planets also have something called an ionosphere, which is a layer of charged particles, or ions, created by the interaction of solar radiation with atmospheric gases. This layer affects radio wave propagation and can influence a planet's magnetic field interactions. The formation of an ionosphere involves the absorption of solar ultraviolet and X-ray radiation, which ionizes atoms and molecules in the upper atmosphere, leading to a region rich in free electrons and ions. The behavior of a planetary atmosphere is governed by fundamental gas laws, which relate temperature, pressure, and density help us understand the atmospheric conditions and dynamics, such as weather patterns, climate changes, and surface-atmosphere interactions on each planet. For example, a higher atmospheric pressure on Venus contributes to its extreme greenhouse effect, while the low pressure and thin atmosphere on Mars allow for more significant temperature fluctuations between day and night. Atmospheric pressure decreases with altitude as there are fewer gas molecules to exert force in the upper layers of the atmosphere. Temperature variations within an atmosphere can lead to weather phenomena, such as the intense storms observed on Jupiter or the dust storms on Mars. Beyond the planets and their moons, the solar system is also home to a vast number of smaller bodies, like asteroids, comets, and interplanetary dust, which tell us how the solar system formed. Asteroids, which are often described as the rocky remnants from the solar system's early days, are predominantly found in the asteroid belt between Mars and Jupiter. These celestial boulders vary widely in size, from tiny pebbles to objects hundreds of kilometers in diameter. Their compositions can reveal much about the conditions in the early solar system, with some asteroids being rich in metals, others in carbon, and yet others in silicates. The diversity in their makeup points to different origins, some having formed closer to the Sun and others in colder, more distant regions. Comets, or the icy wanderers of the solar system, are composed of dust, rock, and frozen gases. When they approach the Sun, their ices vaporize, releasing gas and dust to form a glowing coma and often a tail that always points away from the Sun. Comets are primarily distinguished by their orbits: short-period comets, which originate from the Kuiper belt beyond Neptune and return to the inner solar system at regular intervals, and long-period comets, which hail from the distant Oort Cloud and may take thousands of years to complete a single orbit. The Oort Cloud and Kuiper belt are crucial to understanding comet origins. The Oort Cloud, which is a vast spherical shell of icy objects, is thought to surround the solar system, a leftover from the original cloud of gas and dust, known as the protoplanetary disk, from which the Sun and all the planets in our solar system formed. When the solar system was just beginning to take shape, this disk of material started to come together under the force of gravity to form the Sun at its center, with the planets forming from the remaining material. The Oort cloud consists of the bits and pieces that didn't get incorporated into the Sun or the planets and were pushed out to the far edges of the solar system. Comets also come from the Kuiper belt, which is a donut-shaped region beyond Neptune and densely populated with icy bodies, including Pluto. These regions supply the inner solar system with comets. Another fascinating element in our solar system is the interplanetary dust. It is a byproduct of asteroid collisions and comet disintegration. This dust scatters sunlight, contributing to a faint, diffuse glow visible in the night sky called the zodiacal light. The distribution of interplanetary dust traces the movements of comets and the gravitational influences of planets. As we study the distribution and movement of this dust and the objects in our solar system, we're essentially looking back in time. But how is time even measured in space? Historically, time was measured by the apparent motion of celestial bodies. The sun's journey across the sky defined the day, its yearly cycle marked the seasons, and the moon's phases determined months. Ancient civilizations built elaborate observatories like the Stonehenge to track these celestial movements. With the invention of mechanical clocks, time measurement became more precise, yet still bound to the motion of the Earth. Mean solar time averages the variable solar day over a year and became the foundation of civil timekeeping. Each day was divided into 24 hours, though the length of an hour varied until the adoption of fixed-length hours. In 1582, the Gregorian calendar introduced by Pope Gregory VIII corrected the Julian calendar. The Julian calendar was introduced by Julius Caesar in 46 BCE and was based on a 365.25-day year, assuming a leap year every 4 years to account for the extra quarter day in the Earth's orbit around the Sun. However, the actual solar year is approximately 365.242 days, which is slightly less than the 365.25 days. And over centuries, this small discrepancy caused the Julian calendar to gradually drift out of alignment with the solar year, affecting the timing of the equinoxes and, consequently, the calculation of important dates. The Gregorian calendar reform corrected this drift by introducing a more accurate leap year system. It specified that a year is a leap year if it is divisible by 4, except for end-of-century years, which must be divisible by 400. This adjustment reduced the average year length to 365.2425 days, closely aligning the calendar year with the solar year and stabilizing the equinoxes dates. This correction ensured that the calendar remained in sync with the Earth's seasons and astronomical events over long periods. Building on the need for standardized time measurement, aligning local time with the mean solar time of meridians was a massive step forward. Initially proposed to standardize railway schedules, time zones were adopted internationally at the Meridian Conference in 1884, establishing Greenwich Mean Time or GMT as the reference. Each zone spans 15 degrees of longitude, adjusting local time in hourly increments from GMT. Almost a century later, the quest for even greater precision led to the development of atomic clocks in the 20th century, which measure time based on the vibrations of atoms, specifically the cesium-133 atom. The definition of a second was refined to 9,192,631,770 vibrations of the cesium atom, which is used today. This is because it has a very stable and consistent frequency when it transitions between two specific energy levels and relatively immune to environmental changes, such as temperature and magnetic fields, making it reliable for timekeeping under various conditions. This is how we keep track and communicate with missions through the solar system with precise time measurements that help in navigating spacecraft and in the accurate timing of signals sent to and received from distant probes. The rotation in orbit of Earth is important for keeping track of time. But how did we know the Earth is rotating in the first place? The rotation of Earth is observable through several phenomena, with the Coriolis effect, the daily rising and setting of stars, the gradual shift of constellations over seasons, and the predictable paths of planets, provides clear and observable evidence for the Earth's rotation on its axis and its orbit around the Sun. But the Coriolis effect is a deflection observed in the motion of objects when they are viewed in a rotating reference frame. On Earth, this effect becomes evident in large-scale atmospheric and oceanic currents. It causes cyclones to spin clockwise in the southern hemisphere and counterclockwise in the northern hemisphere, a direct consequence of Earth's rotation. We also know the Earth is tilted because of the changing seasons. The axial tilt, approximately 23.5 degrees, causes different parts of Earth to receive varying amounts of sunlight throughout the year, leading to seasonal variations in temperature and weather patterns. During the summer solstice, the hemisphere tilted towards the Sun experiences the longest day and the shortest night of the year. The Sun reaches its highest point in the sky, and the solar radiation is more direct, resulting in warmer temperatures. Conversely, the winter solstice marks the shortest day and the longest night in the tilted-away hemisphere. The Sun's path is lower in the sky, spreading the solar radiation over a larger area, and thus the temperatures are colder. The equinoxes occur when Earth's axis is not tilted towards or away from the Sun, resulting in nearly equal day and night lengths worldwide. These transitional periods herald the beginning of spring and autumn. The axial tilt of the Earth not only gives rise to the changing seasons, but also plays a crucial role in the transfer of energy. The transfer of energy within planetary atmospheres can tell us a lot on the environmental conditions that are on different planets. On Earth, these include convection, radiation, and conduction. Convection is a key mechanism in the transfer of heat within planetary atmospheres and oceans. It occurs when warmer, less dense materials rise, while cooler, denser materials sink, creating a circulating flow. This movement can create weather phenomena such as winds, storms, and the vast ocean currents that regulate Earth's climate. Conduction is the transfer of heat through a material by direct contact of its particles. In planetary contexts, this is most relevant in the transfer of heat from a planet's surface to the lower layers of its atmosphere or within the solid crust of terrestrial planets. Radiation is the transfer of energy through space in the form of electromagnetic waves. In planetary atmospheres, the sun's radiation is the primary source of energy, heating the surface and atmosphere. Planets, in turn, radiate energy back into space, with greenhouse gases trapping some of this outgoing radiation, thus warming the atmosphere. This is measured by solar insolation. Solar insolation refers to the amount of solar radiation received by a unit area of a planet's surface. It varies with latitude, the angle of the sun above the horizon, and atmospheric conditions. Insolation drives the temperature gradients that lead to the development of weather systems and influences long-term climate patterns. Regions receiving high insolation, such as the equatorial areas, tend to be warmer, influencing global atmospheric circulation patterns that distribute heat from the equator towards the poles. Variations in insolation, due to factors like Earth's orbital changes, can lead to significant climate variations over geological timescales. Polar ice caps are particularly sensitive to changes in solar insolation. During periods of high insolation at the poles, ice caps can melt, contributing to sea level rise. Conversely, reduced insolation can lead to ice cap expansion. This dynamic plays a crucial role in Earth's climate feedback mechanisms, where, for example, white ice surfaces reflect solar radiation based on the albedo effect, potentially cooling the planet further when ice caps are extensive. In the solar system, there are also about 300 known moons, and just like the planets, they have their own orbits and rotations. Our own moon's rotation is synchronized with its orbit around Earth, a phenomenon known as tidal locking. This means the same side of the moon always faces Earth, creating the near and far sides of the lunar surface. This unique rotational characteristic arises from the gravitational interactions between Earth and the Moon over billions of years. The phases of the Moon are a direct result of the Moon's orbit around Earth and the sunlight it receives. As the Moon travels around Earth, different portions of its surface are illuminated by the Sun. The Moon's absence of a significant atmosphere is due to its low gravity, which is insufficient to retain volatile compounds. This lack of an atmospheric blanket exposes the lunar surface to intense solar radiation during the lunar day and the deep cold of the lunar night. The absence of weathering processes that an atmosphere would provide leaves the Moon's surface covered in a layer of dust and craters. However, several moons in our solar system have thin atmospheres, also known as exospheres, but only a few have substantial atmospheres, the most notable being Titan with its dense atmosphere primarily composed of nitrogen with methane and other hydrocarbons. It's the only moon in the solar system with a thick atmosphere and is known for its complex weather systems, including rain and possibly methane lakes. But if we zoom out, our solar system is just a tiny dot in the entire Milky Way. However, as we study the stars and their planets, we learn more about ours as well. The study of stars involves examining the light or electromagnetic radiation they produce and the light they emit. Astronomers use telescopes equipped with various detectors to capture this light, from visible wavelengths to radio, infrared, ultraviolet, X-rays, and gamma rays. Each wavelength provides unique insights from the composition and temperature of a star to its age, distance, and motion. Spectroscopy, the study of the spectrum of starlight, helps to determine a star's chemical composition, temperature, density, and even its velocity in space by observing the absorption or emission lines within its spectrum. These lines, unique to each element, show stellar atmospheres. For example, our Sun offers a detailed glimpse into stellar structure and dynamics. At its core, nuclear fusion converts hydrogen into helium, releasing the energy that lights and warms our planet. Surrounding the core, the radiative zone transports energy outward through the emission and absorption of photons, a process taking millions of years. Above the radiative zone, the convective zone circulates energy to the surface through convection, much like a boiling pot of water. Here, Rising hot plasma cools as it reaches the surface, then sinks back down to be reheated and rise again. The photosphere, which is the sun's visible surface, is where light escapes into space. It's marked by granules and sunspots, regions of intense magnetic activity cooler than their surroundings. The chromosphere and corona lie above the photosphere. The chromosphere, visible during solar eclipses, glows with a reddish hue, while the corona extends millions of kilometers into space. Its million-degree plasma is visible during total solar eclipses. These characteristics provide a detail model on how we can understand other stars in our Milky Way, which we study through a combination of direct observation and indirect measurement techniques. For example, we were able to discover star clouds, which are vast assemblies of stars, and nebulae, clouds of gas and dust that are integral components of our galaxy and where new stars are born, and the interstellar medium, which is composed of gas and dust and fills the spaces between the stars. It also plays a critical role in the life cycle of stars, from the collapse of gas clouds to form new stars to the distribution of elements in supernova explosions. Recent advances, including space telescopes and long baseline interferometry, have allowed astronomers to map the structure of the Milky Way, identifying its spiral arms, central bulge, and the supermassive black hole at its core. These incredible technological strides remind us of the boundless curiosity and resilience in the human spirit as we move forward in this endless journey of exploration and wonder in the universe.